let's step back for a moment and consider all options for substitution. Let's start at the bottom in this graph. That is the least efficient one. It's a non-material substitution. Basically, we compensate material consumption by an increase of non-material factors such as work and energy. Next, we can substitute by quality. We produce products with lower quality and performance, and by this reduce the use of strategic materials. Functional substitution is of course already more interesting. A new product substitutes another product, provided it fulfills the same function. An important example we find in mobility. The combustion engine is substituted by an electric motor. The motor needs two essential components. It is a battery and the high-performance magnet. Every battery needs a magnet. The stronger the magnet, the more torque is generated and less battery is needed. Another example is lighting. Heavy rare earths containing energy-saving lamps have been surprisingly quickly replaced by LED lighting. And what about refrigerations? Since 120 years we use gas vapor compression-based cooling. Substituting this technology by energy and climate-friendly magnetic cooling would result in completely new material demands. Next is technological substitution. For example, can we reduce material consumption by a new process, by additive manufacturing? Can we substitute simple erosion cutting from the bulk piece to create a complex shape by building the complex part layer by layer by additive manufacturing? And then material substitution. I come back to that. For example, the chemistry of the cathode material of lithium-ion batteries is evolving quickly, leading to changes in the need for certain metals. Now we look at the substitutability of elements. Material complexity has increased significantly over the last decades and years. This observation stands actually in contrast to some extent to recycling and circular economy concepts. As said, the scarcity of the elements increases quickly with their intensified utilization. The challenge for a material scientist is to design new and better materials, this under the constraints in resource availability, which means we are searching for substitutes or replacements based on Earth's abundant elements. Substitution is first the balance between product performance and price. Then we should of course consider the ecological footprint given by the life cycle analysis, LCA, or the life cycle costing, LCC. So a second best material in terms of performance might very well be an excellent substitute material, because supply risk and production costs are much lower. However, this can only be fully assessed when the cradle to cradle or cradle to grave cycle is known in terms of material, energy and CO2 in and outputs. The graph here shows a periodic table of substitute performance. The results are scaled from 0, that is blue, or 100, that is red. Blue 0 means that we can substitute the element for all major uses sufficiently. 100 means that no substitute with an adequate performance exists for any of its major uses. So the graph is an observation of the moment, but it shows clearly how difficult it is to find adequate substitutes for many elements and applications. But we also have very successful examples. In the 1970s, in and after the civil war in Zaire, a sharp increase in the cobalt prices or a sharp decrease in the cobalt supply was observed, which led to enhanced research activities and the discovery of the neodymium iron boron high-performance magnet, which is still, till to date, the most powerful magnet at room temperature.